Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist Tea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire aspiring geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Scher, and this month we're talking with Libby Sharman about sulfate recycling at subduction zones. Libby Sharman is the technical lead at BHP Explorer. Libby, welcome to Geochemistry.
Thanks so much, Sam. It's fantastic to finally get an opportunity to join you. A big fan of the podcast for a long time, and especially for bringing me back to sulfur isotopes after quite a few years away. So glad to be here.
I'm not going to thank you for bringing me back to sulfur isotopes, but same. And also, interestingly, even though every single podcast has had a female representative in myself, you are also our first female guest. So, yeah, nice to have you.
Brilliant.
For all of our listeners out there, I just want everyone out there to know if it adds to your life or not. But Libby and I met when she TA'd me in metamorphic petrology while she was a PhD student in economic geology and isotope geochemistry at McGill University. Since then, she's gone on to work in various geology and scientific communication roles before she started working at BHP as their principal global geoscientist, then superintendent geology for Canada, and finally as the technical lead for BHP Explorer. Libby, this was a heavily condensed version of your career. How and why did you get into geology, geochemistry? Take us through it.
Yeah, it's definitely a condensed version, but long story short, I was that kid with a rock collection. I have loved rocks and minerals and learning how the world works since I was a kid. I finished my high school education in South Africa, and so going on to study geology was a really obvious choice. I will admit, originally I wanted to be a geophysicist, and on the
Ooh.
open day at WITS, it was sold to me as, well, you can either have a donkey and a backpack or you can have a helicopter. As it turned out, let's just say that physics and mathematics aren't exactly my strong suits, whereas geochemistry and geology was definitely where I enjoyed to play. And so when I was looking to specialize towards the end of my undergraduate career, geochemistry was where it was at. And liking the applicable nature of geochemistry and economic geology, it was a really obvious combination.
I have to agree with that. Not that I ever necessarily considered geophysics, because also perhaps my troubles with physics and mathematics, but I
I'm
love how
also
that's
happy. I'm also happy to say I have not yet had to work with a donkey, although there have been helicopters in my career.
helicopters are neat. Definitely the best part about being a geologist, especially being a geologist graduating in Canada, where it just that's the norm, which is so bizarre.
It's pretty wild when you say that to people, that your day
Yeah.
job is going out in a helicopter. But yeah, so that geophysicist way back when was a little bit underplaying the role that those would have.
Indeed. So then, while starting out, as you've mentioned, as a humble geochemist, and as we talked about a little bit in your condensed bio, you've migrated into many different roles in your career. And so I'm just looking for right now any advice to some listeners, maybe an academic interest in geochemistry, but unsure really of taking the plunge at a master's or a PhD in it because they don't know how employable they'll be. And they're, I guess, more so afraid of pigeonholing themselves.
Yeah, this is a really interesting question. And one of the things I did actually ask my husband this question because he is also a geochemist, and we had a good chat about that this morning. But one of the great things about being a geochemist is, especially in exploration and the minerals industry, is you are the opposite of pigeonholed. You are going to be the person who is looking at data and contributing to multiple different projects at the same time. You really get to have a line of sight across everything that's happening in the business, as opposed to a project geologist who usually will commit themselves to a couple of projects to be really focused and working on over a few years. So it's a really fun one to be that sort of subject matter expert in the field of geochemistry. And there's not a lot of us out there. I will admit that I probably consider myself a little bit of a lapsed geochemist these days. I don't do a lot of geochemical data analysis anymore. but they are a rare breed, and in both on the academic side as well as in industry. So definitely very employable. The one thing I would always say, and I talk about this a lot actually with the explore cohort, is with whatever you're doing with geochemistry, always try to relate it back to the rocks and the minerals and ask yourself the why. What is the story that you're seeing in the data, and how does it impact the decisions that are going to be made by the business? Because that is really one of the key roles in geochemistry. And I think something that's sometimes a little bit underplayed.
I love that answer. And I think as well, I could imagine anyway, people coming to you maybe at Explore with all these different projects, you having a look through. So now you're in this more of a management role, but you're able to see the raw data in a sense and be like, well, they are trying to take us for a ride here because what they're saying here doesn't make any sense. So I feel like that could be something that people could think of maybe as well, just how they could use it
Yeah,
maybe later on.
100%. Yeah, definitely. Definitely.
Cool. That's a bit of a different kind of introduction than we've had in the past. And I think that this answer is pretty pertinent because I think everybody's always afraid of kind of pigeonholed, but at the same time, if you have the geochemistry in your blood, I mean, just go for it.
And not necessarily to say that if you are a geochemist that you need to go into exploration or mining, but it is obviously a fairly large employment pool. But really, we're seeing with deposits being undercover, with things being harder to find, being able to pull the most out of the geochemistry data that we gather, and whether that's lithogeochem or isotopes or uh, zircon trace element geochemistry, the potential of geochemistry to have significant impact on the discoveries of the future cannot be understated. And companies are realizing this. The need for well-trained specialists is just going to get bigger and bigger.
Yeah, and I would add to that just for our listeners as well. I've had conversations with some more of a data science type companies, and their answer has been along the same lines as you, Libby, just in the sense that they see that the role that geochemistry is going to be playing in the future to be more and more as we continue to go undercover. So neat. Well, I just want to thank you for sharing this journey with us, but now it's time for definitely my favorite segment, tea time. So the kettle's hot and it's time for you to spill.
This is a segment I was looking forward to, and I still actually don't know what I'm going to say here.
I love it.
I thought I'd take an opportunity to talk about how I got into sulfur isotopes, because actually my master's and PhD were both on using multiple sulfur isotopes, so 33, 34, and 36 sulfur, in understanding ore forming processes. And this all came about when I was in my honors year at WITS, and we had a group from Maryland came and visited, and they had been doing this cutting edge work on multiple sulfur isotopes and what it was telling us about the evolution of oxygen in early Earth's atmosphere. And they were going out to the Deutschland Formation, which is a very famous sedimentary formation in South Africa, which represents the Great Oxidation Event, and they were going to take some samples. And I was sat in the audience, and my honors project at the time was on this area of the Bushveld Complex called the Platreef. And the Platreef had been mined by Anglo-American for quite a few years, but a new kid on the block, the Ho, had come in and was doing some exploration, and they discovered some pretty massive sulfides. And we were trying to figure this all out. And one of the key things about the Platreef is that it cross-cuts the Deutschland Formation. So it actually cross-cuts this significant stratigraphic point in Earth's history. And I'm sat there and I'm thinking, well, why the hell couldn't you use multiple sulfur isotopes to figure out where the sulfur is coming from in the Platreef? Because it's going to be changing across the length of the intrusion. And so me being me and an honors student wandered up to the researchers at the end of the talk and shared this idea. And they were like, well, I don't know why it would work, but I don't know why it wouldn't. And so they're like, have you got any samples? And I'd been doing sulfide separates at the time. And so toddled off and gave them some little vials of sulfide separates to take back with them to the US. They got through airport security, no problems. And a month or so later, I got an email back with this very excited message saying, there's mass independent fractionation of sulfur in the Platreef. Oh my God. And that was the first use of multiple sulfur isotopes on an ore deposit. And it worked. And that was a significant topic for my master's and actually my PhD as well. So it's funny, you never know what you're going to learn in a talk. and you never know what idea you're going to have and where it's going to take you in your career.
I think I'm just sitting here stunned because number one, I just feel like what does multiple like mass fractionation even mean at this point because I'm so many years out of university and I just blocked it all. So I think we're gonna have to expand on that one really quick for me to be like, oh my God. But then also, oh my God, that sounds so cool.
So this is the thing, listeners. There's geochemists and then there's isotope geochemists.
You were listening to one of the former and the latter.
So, I mean, super quickly,
Yeah,
and this
please
is,
do because now we're interested. Now we're down the rabbit hole.
yeah, and this is like you're making me remember my PhD, and my PhD was a very long time ago. But essentially, you have four isotopes of sulfur: 32, 33, 34, and 36 sulfur. And in most processes, geologically and biologically, sulfur fractionates according to its mass. So the heavy sulfur will preferentially fractionate. In some processes, the light sulfur will preferentially fractionate, but it's always controlled by the relative mass of sulfur. Except, as it turns out, in the Archean atmosphere, where certain wavelengths of solar radiation created a fractionation of sulfur that was independent of mass. And what you can do is figure this out by measuring the different isotopes and then seeing where they should relate to each other if they're fractionated by mass. And if they fall off of this mass dependent fractionation line, you then say they're independently fractionated. And what's cool about this is because that independent fractionation only happens in the Archean atmosphere, and then it gets preserved in sedimentary rocks that form during that same period, you can use it to see when you have crustal sulfur contributing to your geological processes.
Okay.
And that transition from mass independent fractionation to mass dependent fractionation in the Archean atmosphere happens with the rise of global oxygen. Creating an ozone layer stops those particular wavelengths of solar radiation from coming into the Earth's atmosphere, so you don't see the signature anymore. It's a really neat way of tracking that. And then what it also means is, and this is interesting for the paper we're going to read, normally when we look at sulfur isotopes to understand sources of sulfur in ore deposits, you look at delta 34 and it's a histogram, and you compare it to other single value or ranges within different things, which statistically isn't the best way of necessarily trying to come up with an answer, and you've got a lot of potential answers to things. But if you use delta 34 sulfur and the mass independent sulfur value, all of a sudden you're on a binary plot. And binary plots are so much more useful for giving you information for where sources are coming from and what's contributing to a particular magma or something like that. The only downside is it does only work in rocks that have interacted with Archean sediments.
Okay. So in the end, what did just maybe you've already said it, but I've like already lost track because I've learned so much from like 5 minutes ago. What did that mean in the context of the Platreef?
So for the Platreef, what it allowed us to do was actually demonstrate that there was mass independent fractionation of sulfur preserved in the Platreef intrusion and the sulfides. Previous researchers had thought that all the sulfur was coming from a dolomite carbonate rich unit, which was younger and so didn't have that mass independent fractionation. But because we had that signature in the sulfides in the intrusion, we were able to say that there was actually a significant contribution of sulfur coming from sulfidic black shales that were not in direct contact with all of the rocks, so that we then knew there must have been a contamination event of the magma somewhere else at depth prior to final emplacement. And so that gave us a really good insight into the different processes that led to the
Neato.
formation of the Platreef.
All right. I don't know, listeners, how you guys are doing, but now I feel like I'm caught up to speed. And actually, this is a really good bit of tea. I love it. I love it. And I feel, yeah, like I feel nice and limber and ready to go for our paper that we're going to talk about next. For this episode, we read sulfate recycling at subduction zones indicated by sulfur isotope systematics of Mesozoic ultramafic island arc cumulates in the North American Cordillera by Dragovich et al. 2023. Libby, could you start us out easy? I think we've already gone there. I guess we've had that easy part a little bit before, but my original question was why you're so interested in sulfur isotopes and even isotopes more broadly. Is there anything more that you want to add to why you like isotopes so much?
Yeah, I just think they're an incredibly powerful tool in the geochemist's toolbox that when they're used appropriately, and I'm going to say that because I think isotopes are used inappropriately quite a lot. But when isotopes are used appropriately, and whether it's stable isotopes, radiogenic, metal isotopes, they can be incredibly powerful at understanding what's going on in an ore forming system or in a geological environment. They're just really interesting, good tools to have in your toolbox.
We're talking about ore deposits here, and I know that there's so many different ore deposits out there. Let's say because me and you, we work a lot in a porphyry copper world, what would be, say, your favorite isotopes to go and use for that, just for flavor?
Ooh, I think it would have to be uranium lead because we can do age dating on zircons in porphyry environments, and that helps us understand the prospective ages of intrusions within porphyry belts.
And why perhaps would we not be as interested in potassium argon?
Potassium argon is more prone to resetting in subsequent events. So the uranium lead in zircons is really quite tightly held and it's very difficult to reset that systematic. So it gives you a very good, confident age date. Whereas a couple of the other ones are prone to resetting in metamorphic environments and things like that. So you just have to be a bit careful with how you use them.
Love it. Always love to go back to my porphyry coppers. So cool. I
Well, we're
think,
going to get there again in the next question. I'm holding out on the listeners
okay.
because I'm excited with where we're going.
I feel like I need to do like another stretch here. So just give me, okay, one arm, the other arm. Here we go. So to the geochemistry crew, I'm not going to lie to you here. A big interest that Libby and I had with this paper is that there is a good McGill alumni narrative here, which honestly, Libby and I are continuing both as McGill alums by talking about this paper. So you guys can just add us on to the end of the et al. Here for this paper. But that said, one thing that immediately jumps out to me in the abstract is that we're going to be talking about sulfide saturation and oxidized magma. I get a little hints of Don Baker, one of our professors here. But anyway, Libby, why is this concept important from an economic geology perspective?
Yeah, so this is a super fun one. And it's funny because the paper itself talks about ultramafic intrusions,
Yeah.
which are typically associated with nickel mineralization, although the intrusion in question doesn't have a significant amount of mineralization in it. But what's more interesting about this paper is it presents really compelling evidence for the transfer of volatiles, sulfur in particular, from subducting slabs into the overlying mantle wedge. And this is a pretty big deal because there's been a lot of debate around what creates fertility for porphyry copper deposits in subduction zones. And there's been an amazing body of work done by Laux and others that talks about compressive regimes being really important in the mash zone where magmas are held prior to final emplacement and how that drives oxidation state and creates these magmas that are better for forming porphyry deposits. It's to do with the carrying capacity of copper and the concentration of copper in the magmas. But a component that has been debated is how much of an influence the composition of the subducting slab has on the capability of that overlying mantle wedge and mash zone to reach fertile oxidation state. And there's some people who don't think there's any contribution, and then there's some people think that there has to be. And the paper talks about the evidence of quantities of sulfur in degassing volcanic magmas and things associated with arcs, but previous studies had a lot of trouble identifying any categoric contribution of a sulfur volatile into those mantle wedges. But this paper says that it's happened, that they've got this data that says it is occurring. So you are seeing that transfer of volatiles. And where this gets super interesting is that you look at somewhere like the Tethyan, for instance, And the paleotethers, and this is work that Jeremy Richards published quite a few years ago, the paleotethers and the subduction related to the closure of the paleotethers doesn't have a lot of big porphyry deposits associated with it. Whereas as you get into the mid to neotethers closure, you start to get some really decent sized porphyry deposits, some real world class systems. And what Jeremy proposed was that because in the early stages of the closure of the paleotethers, you were subducting deep ocean sediments, organic rich black shales, really reduced environment sediments, that you were then going to have way more trouble because the volatiles you were giving off would be reduced. You're going to have a lot more trouble getting that magma to an oxidized state to make it fertile for porphyries. But then as you go through the closure of the paleotethers, you then verge into more of an oxidized slab that's being subducted. And so you'll find it easier to get to that oxidized state of the magma through the compression. And that means you've got a better chance of forming a big porphyry deposit. And it's reflected in what we see in the rock record and the known deposits that we've identified. And so, but this was something that was pushed back on because we didn't have the evidence of that volatile transfer from the slab to the mantle wedge. And this paper actually speaks to that, although they don't actually go there in the paper because they're talking about an ultramafic deposit.
So I think Dayon and et al., everybody, that you now have a new thing that you have to do is something to add on to the paper. That's so interesting. I never really thought of it that way, but I think also because I focus so much of my work since I entered industry on working in Latin America deposits that I and not that I should have ignored other research, but I skipped over, even though the tethene, those deposits interest me so much. I just haven't read so much about them. So I think it's really cool with your more global perspective that you were able to make those linkages. And that's pretty cool. I didn't think of it that way. And maybe that's why you spent a little bit longer than I did reading this paper. Because you're like, well, what Jeremy said. I love that.
Well, I am not going to lie, listeners. I had to look up a couple of words in the paper. It was definitely one that took careful reading.
Yeah, it's not too long to those who have read it. And Libby and I talked about this a little bit before recording, but there's something about igneous petrologists and the words that they use that require definitely having a dictionary side by side. So don't feel bad. We're all in the same boat. So then the whole introduction, geologic background section, for me, I was thinking this is very Don Francis. So going back to the McGill alumni narrative, Don Francis is a professor. Is that the right word?
Yep, I think
I don't
that's
think
what.
my Latin's very good, but anyway, you guys can correct me if that's not how you pronounce it. But Don Francis was one of my professors, and he was just a giant in igneous petrology, and Diana was one of his students. To set up our story and journey into sulfur isotopes, could you give our T crew an overview of the geologic setting here and speak to why this is such a good setting for which the researchers were able to investigate their questions on magmatic versus country rock source using the sulfur isotopes?
Yeah, I'm not going to try to go too much into the geological setting in
Sure.
detail. There's a good introduction in the paper, and from reading the paper, there is actually another published paper on this intrusion that it probably would also give you a lot more information. But there's a couple of key pieces to why they did what they did here. And what it is, to go back to that challenge of why people have struggled to get evidence of volatiles within mantle wedges above subduction zones and in arc magmatism, is because usually what happens is as magmas rise to the surface, they degas. They lose a lot of the signature that you might be able to look at to figure out where that sulfur and oxygen and other things came from. So looking at volcanic magmas or volcanism, things like that aren't going to help always because you're not preserving the primary signature. What is different about this intrusion is that it is actually come in at depth and been preserved at depth, and it's fractionally crystallized at depth without degassing. So it's preserved a bunch of the primary signatures at its emplacement depth. And this allowed Dragovic et al. To take these sulfur isotope measurements and get these signatures of immiscible sulfide that formed very early on. The other thing that they've done, the paper talks about different mineral analysis. So they did sulfur isotopes on chalcopyrite, pyrrhotite, and pyrite, and looked at the morphology of those three. And the chalcopyrite's very much interstitial, doesn't look like it's been messed around a lot. The sulfur isotope ranges aren't very big. So it's a really good indication that there hasn't been any secondary influence on them. It's just a really good example of how it's a really good natural laboratory for finding the answers that they needed. And it's a setting that's not unique, but there aren't many in the world where those intrusions have been preserved like that.
Chatting about how they sampled the chalcopyrite, the pyrite. One thing, as somebody that did do a lot of work with sulfur isotopes, that I'm thinking, is there, in a typical study, would you have sampled all of those different sulfide phases, or is one considered better than the other, or is it more of that kind of thing where we're going to sample them all and we'll see which one is is the best for our study? Is there a reason why they took all three? I guess is really the question.
Yeah, so you do usually want to sample every sulfur bearing phase in a particular sample that you're trying to understand, because you're going to get different information out of them. In the case of this study, the chalcopyrite, as I said, was very much an interstitial chalcopyrite within a crystallized intrusion, whereas the pyrrhotite and pyrite had a morphology that looked like they had been recrystallized and mucked around with a bit during metamorphism and subsequent sort of alteration. So what was allowed to happen by taking the sulfur isotope analyses from all three of the different minerals was that the authors were able to see the differences. The chalcopyrite had a very specific signature that was pretty consistent throughout all of their samples with a very small range of data. Whereas the pyrrhotite and pyrite showed pretty big ranges in sulfur isotope numbers that were coming out, which implied some sort of recrystallization and remobilization of sulfur. And that's the kind of thing that, while you could probably start to hypothesize that looking at the morphology of the sulfides, actually having that data, the sulfur isotope data to support it, really enhanced their understanding, and then being able to see how they compared to each other. And then the other thing that they did, which is really important in this study, is they sampled sulfides within country rock to be able to see whether there was a input of sulfur from an external source. And they were able to, certainly for the case of the chalcopyrite, discount that there had been any kind of external input of the sulfur into those chalcopyrite grains.
I have two competing questions. I don't know which one would be best to go first here, but I think I'm going to backtrack and then say, because now we're talking about the host intrusion versus the country rock. When you're doing these sulfur isotope studies, is it also important to have whole rock geochemistry data? Is it something that's nice to have? How do you really use it? What?
Oh, no, absolutely. Whole rock geochemical data, lithogeochem, all of these things, because one of the most important things in sulfur isotope studies and isotope studies in general is understanding the geological context of what the data is telling you, and the setting of the sulfides and or sulfates within your samples. You really can't tell the sulfur isotope story properly without that context. Things like whole rock geochem data will tell you if you have had contamination from certain sources. It can tell you if there's been alteration, metamorphism, all of these things that, especially in ultramafic rocks, which can be quite cryptic, it's going to give you a lot of information and context that's important for interpreting your results. And there's a section in the paper that I read twice just to make sure I understood it, which was talking through a lot of what the geological context was telling them about how to interpret the sulfur isotope data. So
Yeah, I
I
agree.
if I ever read a paper that just has sulfur isotope data and doesn't reference a whole bunch of backup studies, then I tend to get a bit twitchy.
That's good advice for our listeners because sometimes, especially now, you don't want to hate on any universities, but sometimes there's a lot of pressure to get papers just pushed out. And taking this advice at hand, if you're reading a sulfur isotopes paper that doesn't have petrography, whole rock geochemistry, maybe you should also be a bit twitchy and go and find a different reference for instead of using that one.
Yeah, and it's not to say that the conclusions that those researchers have reached would will not be valid. It's just you've really got to understand the context and the rocks.
One thing that I noticed, and it could be just because there was no corresponding sulfate phases, but I did a very small component of sulfur isotopes in my own master's. And for that, it was pyrite, alunite. So I was looking at sulfides, sulfates. I'm just asking, based on my prior experience, why didn't they require any sulfate phases that were in equilibrium with their sulfide phases? Was I just doing a completely different body of work than what they're doing? Or is that something that they just didn't need?
No, so it totally true that you will normally want to look for analyzing sulfate and sulfide pairs in particular and phases, sulfate phases within a sample. But it goes back to that degassing thing. So what happens often is as the magma ascends, you get this separation of those phases. And what that does is creates that fractionation of sulfur with as the phases separate. And so to be able to get an idea of what the original sulfur isotope composition was of the magma, you need to be able to analyze both of those phases and put them back together. The key thing about this project and this research and for them to be able to make the conclusions that they did was that there hadn't been any degassing and they weren't seeing any sulfate phases. So that's actually a pretty important part of the story. But if you do see two phases normally, you would want to sample both of them.
Okay. So now we've talked a lot about the hows, methodologies, but really overall, this paper is about the sulfur cycle and the formation of the Polaris intrusion. It took me a while to get through this paper, and maybe I've forgotten parts of it in between, but could you just explain to us what this meant all in the context of the formation of the Polaris intrusion and also the sulfur cycle in general?
Yeah, it's a really good question and one that I we should have Dayan on as a guest because he could answer this. I should phone a friend. Um,
Yes.
at a really high level.
High level's fine.
High level, so that the Polaris intrusion is a product of magmas that have come from a mantle wedge overlying a subducting slab. The intrusion itself was placed at a depth where it didn't significantly degas, and it then crystallized slowly. And actually, what triggered the formation of the immiscible sulfide liquids in this case was the formation of magnetite. So when you start to crystallize magnetite, you change the FO2 conditions of the magma, and that can lead to an immiscible sulfide forming. And so this is what happened. And we know that there was no external contribution of sulfur because it's not reflected in the sulfur isotopes, it's not reflected in the petrography work that was done or the geochemistry. And then at some point, through tectonics, the intrusion itself was uplifted, eroded, there was some modification of the sulfides in the intrusion, but only the conversion of pyrrhotite to pyrite because during alteration you lose iron and sulfur from the system. But because of chalcopyrite and its crystal structure, it is a lot less prone to that conversion. And so they didn't see any evidence in the petrography that the chalcopyrite had been modified or in the sulfur isotope. So as I said, they had this really small range of analytical values in the chalcopyrite sulfur isotope data. And was the key thing about this intrusion that allowed them to do the study to assess whether any of the sulfur in any of the sulfides in the intrusion had come from the subducting slab, and the evidence that they present indicates that it did.
And as a curveball to this, instead of asking the one that I have written down as as my last question for the day, maybe more importantly for our talk and us both working in economic geology, what do you see from this body of work having implications for economic geology in general?
I think it's a brilliant, brilliant final question, or maybe not if you decide to spring another one on me. But
No, that's the last one. That's it.
I think it goes back to where I started with this is understanding how our Earth systems work and how various elements and key components interact with each other is incredibly important for understanding ore forming processes. And especially if you think about things in a minerals systems setting where you are really trying to figure out what the processes are that have to have happened to form a world class deposit.
Mm.
This paper speaks to that. So as I said, it has of subducting slab material back up into the mantle wedge. And the knock-on effects that has of the composition of the mantle wedge, how it sets up a source for a porphyry deposit or even a nickel deposit. That's all really important information for where you're going to go on the globe to look for those deposits. So if you're starting at a really big scale and you want to know the best place for porphyries, you're going to say, okay, maybe we don't want to go somewhere where the composition of the subducting slab was more reduced than somewhere else. Because it is going to make it harder. It's not impossible to set up a system for a big porphyry, but maybe it'll make it harder. Similarly, maybe the subducting slab has changed the composition of the mantle wedge. That means you're going to be able to release nickel into a magma more easily. These are all really important things to think about and understand as we're trying to find the next big districts for mineral exploration. So while this paper is a very technically focused paper, the discussion that it drives for how we think about ore forming processes is actually big and quite important.
So are we gonna have a BHP book club now for niche papers like this? I think that that's probably because you make a great point in your final statement there. It's such a niche paper and one that save knowing the authors and passing through it on LinkedIn, I would have never picked up, but it drives this point that maybe that I'm not saying that there's not value in reading igneous petrology papers. I'm just saying maybe it drives this discussion towards do how do we come across papers like this more easily in economic geology and such that we can drive discussions within our teams because something like this very dense, very difficult to get through, but in the end when you have somebody that has knowledge of these things, right, you have knowledge of sulfur isotopes, you being able to share this with all of our listeners, I mean this sounds like a really interesting thing that maybe BHP implements or something, just throwing it out there.
It's a
All the
really
other
good thing.
companies,
Yeah, this is going to be a little bit of a soapbox to end, but
I'm all about the soapboxes.
we're getting to a point where we're going to need the brightest minds that the world has to find the ore deposits that this planet needs for driving us to a net zero future. And part of that is creating an environment where companies allow for professional development and discussions and how you introduce new ideas and new thinking into your day-to-day work. I'm not going to lie, I may not have had time to get to this paper either had it not been for us agreeing rather rashly to talk about it. But it's one of those things that's so important because we need to keep the people who come into geology and geoscience have such a passion for the world and how it works. And keeping people engaged and interested and pushing boundaries and thinking of new ideas is going to be so important to keep those bright minds working in our industry and helping us with ore deposit exploration. And it's also why going to conferences is amazing. One of my favorite things in conferences is to dive into a session that isn't anything to do with what I'm doing. Because the number of times you learn something new and exciting that you can take back to your job, or as you say, having a book club, having a paper discussion group, these things are all really important and they all have to come. I always encourage teams to come up with these things themselves. Like, go for it. This is how we continue to enrich each other professionally, and it's so important.
So important. And whether it's a small mining company or a large one, you get people from all walks of life, from all over the planet. There's such opportunity to learn from people from different places, different times in their life. And here I am talking with you. And even though we went to the same school, we have two very different educations in the sense that I did not specialize in isotope geochemistry. And I probably learned more about isotopes in this hour than I did um, when I did my little alunite pyrite separations for one small piece of the giant puzzle that I was working on. I like this soapbox. It's a good one to end on. With that, I just really want to thank you for so much for being here. And I really hope that this discussion for all of our listeners has been more than just a good alumni narrative from McGill. I want to thank everyone for listening to Geochemistry, and a big thanks to Libby Sharman for being on the show, dishing pretty good tea. That was really cool. And then just taking us on this journey. Thanks to our sponsor, LKI Consulting, and to It's Water and Coma Media for our music. And I'm looking forward to chatting with everyone next month.